Let us start with a chain rule in Calc 1. Calc 1. If you have a function that relies on an input, but the input itself is a function which relies on another input, say h, and then finally that relies on a variable x. So we have, this is just a diagram. I don't necessarily want to put arrows, but this is a diagram that states that f relies on the output of g relies on the output of h, and h relies on the output of x. In other words, another way to say it is that f depends on g depends on h, and h depends on the value of x. If x changes, so does h, and when h changes, that as a reaction causes g to change. As a reaction of that, that causes f to change. So in Calc 1, we saw that the derivative of f with respect to x is the derivative of f relative to g multiplied with the derivative of g relative to h multiplied with the derivative of h relative to x. And the reason why we want to do that is because if we actually nest together f on g and then g on h and x, the expression could be rather complicated, very, very complicated. Instead, what we do is break up a function into elementary or more elementary sub-functions. They're not sub-functions. This is a composition of functions. But we break it up into parts via composition. And then those parts are typically simpler, or we try to break them up into the big functions into simpler functions. And then the derivatives of those simpler functions are usually way, way faster, easier to work with. So there is a chain rule. This is a long chain rule example from Calc 1. Now, in multivariable calculus, multivariable calculus, okay, the diagrams could be way, way, way more complicated. So let me start with example 1. And right now I'm going to show you, first we're going to see 2 or 3 examples of diagrams, and then we're actually going to do an example where we are going to plug in actual operations and numbers. So let's start with an example 1 of what could happen in a multivariable scenario. So let's say you have a function w that relies on 2 functions or 2 outputs, u and v. In turn, u and v rely on s and t, each one of them. In turn, s and t rely on the output of, or the value of x and y, each one of them. All right, so we have a longer chain, 1, 2, 3, 4, 1, 2, 3, oh no, same depth. So the same depth of chain, but now we got more functions going on, and the interrelation between the functions is more complex. Well, here there's no interrelation other than just straight across here. T depends on x, but also could depend on y. And then u depends on s and t, but t depends on x and y, and so forth. So the question is, how do we go about finding the partial derivative of w with respect to x? Okay, ultimately w depends on x and y. You may be asking, well, if that's the case, why don't we just simplify all of this and say w is a function of x and y and be done with that? And again, as it happens back here, the combination, the nesting of one function onto another can get very complicated, extremely complicated. So by breaking the function up into composition pieces, the pieces are going to be way simpler to work with. That's why. So this happens here as well. combining those functions together into one big W, it's gonna give us a big blob that is gonna be too difficult to work with, especially in this kind of chain, and especially if any of those is particularly complicated. So anyway, the chain rule is actually quite straightforward. Figure out all the possible paths to go from W to X. And for each path, we're going to have a term. So one path, for instance, is through U, S, and X. Okay, U, S, and X. So we do partial of W with respect to U. Okay, so here. But then we got to multiply by the partial of U with respect to S. And then we got to multiply with the partial of S with respect to X. That's just one term and we're going to do this for each one of the paths to go from W to X. So there is one, but then we could go UTX. So we're going to add another term, partial of W with respect to U multiplied. Instead of going through S, we're going to go down to T. Partial of U with respect to T, and then partial of T with respect to X. Okay, so we got two paths, that and that, to go from W to X. But then there's more. We could go to X via V. We can go VSX. So we're going to add the partial of V with respect to, rather, the partial of W with respect to V times partial of V with respect to S multiplied with partial of S with respect to X. And then there's one more path. We could go from W, V, T, X. So we start out with partial of W with respect to V times partial of V with respect to T times partial of T with respect to X. So under this diagram, if you want to find the derivative of W, the partial derivative of W with respect to X, we have to take into account all the different channels that get from W to X. For each channel, we're going to have a similar product as this. Now here, up here, of course, Calc 1, it could be part of multivariable calculus. It is a very, very special case. So whatever we learn here applies there, or many things that we learn here gets to be applied here. So here there's just one chain, and there it is. Here, we have to take into account the contribution of U and V to W. That's why you have to have partial of U and V. But then we have to take the contributions of S on U and S on V. So that's why we have those two. And the contributions of T and U on U and V, that's why we have those two. And then the corresponding contributions of X on T and S. Yes. So this is the partial derivative of W with respect to X. We have a similarly, the partial of W with respect to Y has 4 terms, comma, each with 3 factors. Yeah, so we end up with 12 quantities multiplied, well, 3 at a time multiplied together, and then we add those products, and that gives us this. All right, so first I want to practice the diagrams and how to obtain these formulas from the diagrams. So that was example 1. Example 2. Okay, and I started out with a particularly difficult a diagram on purpose. Um, a lot of the diagrams we're going to see are going to be about this or similar to this, about this size. So pretend W relies on X, on Y, and Z. In turn, those three variables rely on U and V. This is a common thing that happens. So, and then X depends on U, and Y depends on V, and Z depends on V. There we go. So there's the diagram. So W is a function of X, Y, Z. So this is a four-dimensional thing going on. And here there's a five-dimensional function going on. The inputs are 2, the outputs are 3. Here the inputs are 3, the output is 1. Okay, so we could find the partial derivative of W with respect to U, or the partial derivative of W with respect to V. Ultimately, W is a function of U and V. How do we go about finding the partial derivatives of W with respect to U with this kind of connection? Well, the partial of W with respect to U would be, okay, so in how many ways can we go from W to U? We can go 1 through X, or through Y, or through Z. So that means we're going to end up with 3 terms. Each term is going to be 2 factors deep. So in example 1, we went 3 factors deep, 1, 2, 3. This is only 1, 2. And we have only 3 terms. So we multiply partial of W with respect to X, partial of X with respect to U, plus partial of W with respect to Y, partial of Y with respect to U, plus partial of W with respect to Z times partial of Z with respect to U. And there we have it. This is short enough that we can write the same thing for V. The partial of W with respect to V is, oh, this is interesting because those 3 are going to be the same. W with respect to Y, the W with respect to Z. What changes is that X is going to be derivated with respect to V, and so is Y, and so is Z. So the partial of X with respect to V, partial of Y with respect to V, partial of Z with respect to V, as opposed to U, U, U. So it's interesting. Do practice this. Let's do a simpler example. Example 3. See, by starting with an example that is really complicated, and even that I could have made it even more complicated, but by starting with an example that is complicated, all the other ones seem so nice. So let's say W relies on X and Y only. So this is a 3-dimensional. And then X and Y respectively rely on S and T. There. So this is too deep. That means that we're going to have terms that have 2 factors each, just like that one. And we're going to have how many paths to go from W to S? 1, 2. So 1 and 2. So that means we have only 2 terms. So the partial of W with respect to S is partial W with respect to X, partial X with respect to S, that's this path, plus partial W with respect to Y, but then we multiply by the partial of Y with respect to S. Yep. The partial of W with respect to T is partial W with respect to, okay, so if we want to go here, we go via X, and then partial X with respect to T. plus partial w with respect to y times partial y with respect to t. And that works out. The next example is an interesting example because it combines partials with regular derivatives. So the next one will be example 5, rather, example 4. Yeah, this is this is easier, but yet it has a little complication to it. So let's say you have a function that relies on x and y, and x and y each rely on t. That's it. That's the whole diagram. So ultimately, f is a function of t. Ultimately, in the previous examples, such as in this one, w was ultimately, well, initially, w in this example 3 is a function of x and y. In turn, x and y are functions of s and t, so w is also a function of s and t. The way this is written is kind of weird because it's not the same formula. So it's not, the w is the function, not the formula necessarily. Let's just put a connector like this. So those two are connected. Yeah. So this function is a function of t. And the question is, well, what is the derivative of f with respect to t going through the x and the y? Well, first of all, because there's only one variable, we're not going to do a partial derivative. This is a regular derivative. So straight d, that means that we have a regular derivative. Okay. Because ultimately f is a function of one variable, as opposed to example 3, where w was a function of two variables. W in example 2 was a function of two variables, and in example 1, w was a function of two variables ultimately. But f is a function of one variable, so we do not ask for partial derivatives, but rather direct derivative. However, the way we figure this out is by going through x, and that is one of the two variables of f. So this is the partial of f with respect to x multiplied with, but x in turn is a function of t, a single t. So this is not a partial, this is a regular derivative of x with respect to t, plus partial f with respect to y times derivative of y with respect to t. So notice that we are combining partial derivatives because f is a function of two variables with regular derivatives because those xy and xy are actually a function of one variable. Ultimately, f is also a function of one variable. So when we say that, we got to be careful with, oops, down here. And even I can even say that here. So when we say that f is a function of x, y, it is true that f is a function of x, y, but also f is a function of t. So we're using the name f, but the formulas are not necessarily, they are the same, but they aren't the same in the sense that this one uses x and y and this one uses t. I think the example, the actual example we're going to work on is going to make things a little more clear. Okay, so example 5. Example 5. Okay, so this one is going to be more of a concrete example. F will be a function of three variables, x, y, and z, and it will be x plus y squared plus xz cubed. In turn, x is the sine of s plus t, and y is the cosine of s plus 2t, and z is equal to 5s minus t. Okay, so we have to explain the relationships that are going on on the function. This, as you can tell, each one of those is already reasonably complicated. Imagine putting this x here, this y there, and then squaring it, this z here, and then cubing it, multiplying it with this x. As you can tell, if we were to just use one function as opposed to breaking it up into parts using composition of functions, this would be way too complicated to handle all in one. Yeah. So instead, we break it up into pieces. Before I ask the question, so this is just the setup of the example. We haven't even finished. But let me just tell you what was going on. F is a function of x, y, and z, x, y, and z. In turn, x is a function of s and t, s and t. So x depends on x and t, s and t. And so does y, and so does t. Rather, so does z. Okay. So that is the situation that is happening right now. And that's why we need one formula that relates f with x, y, and z, one formula that relates x with s and t, one formula that relates y with s and t, and one formula that relates z with s and t. Okay. So the question is to find the partial of f with respect to s and the partial of f with respect to t when s equals pi over 2 and t is equal to 0. So that is the problem. Usually when we give you this problem, we're not going to give you the diagram. The diagram is not going to be given to you. You're going to be given this kind of problem, and you yourself should set up the diagram to follow. All right. So before we start, let's figure a few things. This is a moving output. F is moving because S could vary and T could vary. And as the parts of this situation move, okay, as they move, as S moves and T moves, the derivatives, the rates of change are going to vary because there's no linearity here. So there's a lot of different changes of rate of different kinds. So this is moving. However, there's going to be a point in time when we're going to freeze the whole situation. And we're going to freeze the situation when s equals pi over 2. So I'm going to put a pi over 2 next to the s. I'm going to put the 0 here because eventually we want to plug in those values. But that doesn't mean that those values are going to be there all the time. First, we've got to find the relationship between the moving parts, and then we're going to plug in the numbers. By the way, we can find x. Sine of pi over 2 is 1 plus 0. So again, assume that s is pi over 2 because that's part of the problem, and t is equal to 0. So sine of pi over 2, 1 plus 0 is 1. So we're going to assume x is 1. We're going to assume y, given those conditions, is, where is y? There it is. Cosine of pi over 2, which is 0, plus 2 times 0, that's going to be 0. And then 5 times s, so 5 of those, minus a t, which is 0. So that is going to be, z is going to be 5 pi over 2. And then we're going to have a value for f. It will be 1, so f is 1 because it's an x, plus 0 squared, plus 1 again times 5 pi over 2 quantities cubed. So that's going to be 125 over 8. We're not going to use that output. Let's write it down anyway. So x was 1 plus 0. I'm not going to write this 0 because y squared is 0. And then 1 again, and then z cubed. So that is 125 pi cubed over 8. Again, we're not going to use that output because all we want is the partial derivatives. We don't necessarily want to deal with the output itself. All right. So let's look at the solution. Okay, so the partial of f with respect to s, which is one of the things we want to find. So we want to find that the partial of f with respect to that is the partial of f with respect to x, f with respect to x multiplied with the partial of x with respect to s, plus the partial of y with respect to, I'm sorry, the partial of f, again, f with respect to y times partial of y with respect to s plus partial of f with respect to z times partial of z with respect to s. Okay. The partial of f with respect to x, so let's go back up here, that's f. This, the derivative of this with respect to x is going to be here and here, so that is going to be a constant relative to x. So the derivative of that is going to be 0 because we're adding that. So the derivative is going, with respect to x, is going to be 1. Okay, so this is going to be 1. But then there is more to it because the derivative of this part with respect to x is, again, 1z cubed. So plus z cubed. That's this part. Partial of x with respect to s. There's x with respect to s. The derivative of that with respect to s, well, that is going to be the cosine of s, not plus 1 because we're doing partial derivative, which means that t is a constant. So this is just the cosine of s. Cosine s plus, going back to f, the derivative of that with respect to y. There's just a y there, to y, multiplied by the derivative of y with respect to s. The derivative of cosine is negative sine. T is a constant when we are dealing with s, plus the derivative of this with respect to z. There's a z, so we have 3z squared, and the x should be still there. 3xz squared. And then the derivative of z with respect to s is 5. Boy. Okay, so we got 3 terms. Each term is 2 factors deep. Okay. That is the regular. Okay, this is the partial derivative with its moving parts. If z moves, then this moves. If y moves, then that moves, because it is part, all of this is part of df ds. I'm going to copy this down here, df, partial of f with respect to s. Okay, so we want to evaluate this when s is pi over 2. See, here we gotta, I prefer to be specific because if you just put pi over 2 and 0, we don't know, well, it should be fairly understood because there's going to be only two inputs. But, and the function has 3, but still somebody would have to guess what we mean. If we just put pi over 2 and 0, somebody would have to guess what's going on. So I want to be more specific. I'm going to say that when s is equal to pi over 2, comma, and when t is equal to 0. And that causes a domino effect. You know, when those two are fixed, that fixes those three, and that fixes the function. And that also fixes the partial derivative. All right, so z, well, it's 5 pi over 2. So we end up with 1 plus, that is interesting, we end up with the same as that. I believe that is coincidental. Let me double check something. No, it is coincidental. One, yeah, it was coincidental because there's an x here. So this is really 1 plus z cubed. Anyway, 1 plus 125, 125 over 8 pi cubed. That's just this factor. Cosine of pi over 2, let me think. Cosine of pi over 2, oh, is 0. Oh, so all of that is going to vanish. All of this is going to be 0 anyway. Plus 2y. 2 times 0 because y is 0. So all of this is going to be 0. Let's just finish it anyway. Negative 1 because s is pi over 2. Plus, so this is going to be 0 because of that 0. This term is going to be 0. That's not a 20. That's 2 times 0. And that's going to be 15. X is 1 and z. Okay, so 15 times 1. And the reason why I get 15 is because I'm already multiplying 3 times 5. That is the 15. 1 is the x. Z is 5 pi over 2. When we square that, we end up with 25 pi squared over 4. So again, that is 0. So is that. So the product will be 375, if I'm not mistaken. 25 times 5 is 125 times 3, yeah, 375. So the final answer is 375 pi squared, all of that over 4. Okay. So the partial of f with respect to s, when specifically when s equals pi over 2 and when t is equal to 0, will be 375 pi squared over 4. All right. I'm going to try to squeeze the other answer here. Okay, so that is one solution. And I have this much page to go. Let's see. The partial of f with respect to t, okay, will be the partial of f with respect to x times partial of x with respect to t, plus partial of f with respect to y times partial of y with respect to t, plus partial of f with respect to z times partial of z with respect to t. Now, eventually, we're going to plug in the same values. I got ahead of myself. This partial f with respect to x, partial of f with respect to y, and partial of f with respect to z show up here, so we don't have to recompute those. Although it's not a bad idea to do that because we want to double check. So what are they going to be? 1 plus z cubed, 1 plus z cubed. Derivative of x with respect to t. Ooh, 1 plus. Now we are here. 2y. Derivative of y with respect to t. Oh, just 2. Plus 3xz squared. 3xz squared times derivative of z with respect to t, -1. Okay. Now we want to be specific. We want to plug in inputs. So the partial of f with respect to t, when s equals pi over 2 and t is equal to 0. So now the reader knows what inputs we're using and for what variables. Now 1 plus z cubed, we already computed that back here. That was this big number. The difference now is that we're going to multiply by 1. So this number is not going to go away. We're going to end up with 1 plus 125 over 8 pi cubed times 1. I'm going to omit the 1. Let's not. 1. Okay. Plus 2 times 0. That one will go away because that is not this output 2 times y doesn't change. It is the same. Even though this time we're multiplying by 2, well, we're still going to end up with 0. And then this output, where was that going? So we got this 2, 15 times 1 times, so what is changing now? 3xz squared. So let's see, it's 3, 1. This guy squared, 25 pi squared over, yep. See, that's what I get for multiplying by 5 right away. Now, it's only 3. Instead of the 15, it is only 3, but we're subtracting it. So minus, yep, 3 times, there we go, 25 pi squared over 4. Okay, so that is going to be 1 plus 125 pi cubed over 8. That's going to be 0, and then we subtract 75 pi squared over 4. Yep, so this would be the partial derivative of f with respect to s at s equals pi over 2, t equals 0. So this is this part. And this is partial f with respect to t at s equals pi over 2, comma, t equals 0. Sorry to not be completely open on this. What I mean by that, spread it all out a little bit, but I wanted to keep everything in one page so that I can go back and forth, because we want to refer back to the diagram. We want to refer back to the functions, where the numbers came from. And there we have it. Now, does this look difficult? Yeah, it is. But had we done it without the chain rule, it would be even worse. I'm not going to do it, but I just want to show you what we did not do very quickly. So f of x, no. Sorry, f of st as a function of st would be, man, sine s plus t plus quantity cosine s plus 2t quantity squared plus sine s plus t quantity 5s minus t cubed. Okay, so we could have done this instead. Rewrite f in terms of s and t. You know, there's x, there's x. Rewrite f in terms of S and T. There's X, Y, and Z, and we know what X, Y, and Z are. There's X, Y squared, X, Z cubed. And then we would have to simplify, maybe FOIL that. See, here we would have to FOIL that out, perhaps, if you wanted to multiply it out and put it in terms. Um, and then the question is, all right, so what is the partial of f with respect to s? And then we would have to go through all of this. Well, some of you may say, well, that isn't too bad, cosine, that's going to go to 0. And then we got to use the chain rule here. So 2 times this quantity times the derivative of cosine, which is negative sine. And then but here it gets more complicated. Now we got to use the product rule because both of those pieces have s. And then within each one of them, well, not each one of them necessarily, but yeah, within each one of them, we're going to use the chain rule. So we would have, this times the derivative of that, including the cubic. It gets messy. Can we do it this way? Absolutely, yes, but it can get messy. So typically, not always, but typically uh, more messy. So that's why we use the chain rule in its place. All right, this is the chain rule in multivariable calculus.